Hi, geometry kids. So this is lesson 12-2 on chords and arcs. And you've been familiar with the arcs. We've talked about that. So CD, arc is the same as the angle measure there. Not the length, but the arc itself, as long as it's coming out of the center of the circle. So we're getting more now into chords, and you need to understand what a chord is. A chord could be the diameter, so a chord can go through the center of the circle, but it doesn't have to. Okay? So for example, this is chord PQ. It's a segment. This, get a different color, is arc PQ. Okay, and another example would be this. That's a chord. Or that's a chord. Or that's a chord. Or that's a chord, or that's a chord. It has to go from one side of the circle to the other. That's it. It has to go from one side of the circle to the other. So that just to explain chords a little bit. Now, there's lots of theorems in here that we need to go over. And I'm going to focus mostly on this part because I think in these, the pictures are a little more helpful than the words. So it's basically here saying that if these angles are the same, this angle and this angle, then the segments connecting these arcs are also the same. Okay, we already knew the arcs were, but now we're saying if you connect a segment, which would be a chord, those would be the same also. And then it goes vice versa. If you know you have two chords that are the same, then when you connect them to the center, those angle measures in the middle are the same, the converse. Okay, the next one talks about if you have two arcs that are congruent, there's two arcs and let's say they're congruent, then the arc that they make right here, those are also congruent, those arcs. They're the same exact length. And vice versa. If you are given that the arcs are the same, well then the chords connecting the endpoints of those arcs would also be congruent, the converse. And lastly, now we're going to practice some of this. It's a lot to take in. If it says oh wow, this printing is bad. OE is congruent to OF. Okay, so we have this and this. Then AB is congruent to C. I can't read the book. I gotta get it off of my book. I can't read it. Okay, so 12. Why am I on the wrong section? Okay, it's not 12:7. It is 12:3. Sorry about this delay. 12:2. All right, here we go. Okay, if OE is congruent to OF, then AB, okay, is congruent to CD. That makes more sense. I couldn't see that. Then this is congruent to this. That's assuming that this is the same as this. Now, if you have two chords that are the same length, like this, then the distance of the side perpendicular to it would also be the same. All right. So when we look at this, then let's use some of that. What would this distance be? And why? Which theorem? Okay, so a lot of you might see that and see that that's 16, and that is correct. 36. This is 36. Therefore, the distance from here to here perpendicularly is the same. Which theorem is that, though, that we just looked at? Right. 12:7. That was the 12:7 theorem. Actually, was it the converse or was it the regular one? We were given the chords, so it would be the converse. Now we have more, lots of them in this section. Again, I'm going to get my book out for fear that I can't see what I'm doing here. Oh, I wrote them on my sheet. Okay, it says if AB is the diameter and AB and CD are perpendicular, then, and this is the part that you can't read, it says CE is congruent to ED and arc CA is congruent to arc AD. So you might want to fill that in there on your note sheet. Okay, so now let's take a look at what that means. So if CE is congruent to ED, I'm sorry, if I was reading the wrong thing. If AB is a diameter and it's perpendicular to this chord, then this is congruent to this, and these little arcs are also congruent. All right, 12.9 says, again, if this is the diameter, but instead of it being perpendicular this time, it's saying, what if that was given to you, that this side was the same? Then what can you conclude? That they are perpendicular. And the arcs would be the same too, wouldn't they? And if you're given that AB is the perpendicular bisector of this chord, so we're given different things in these different things. AB is perpendicular. Okay, yeah. Then AB contains the center. So then this diameter has to contain the center. All right, so I need you to right now grab your compass and your little protractor. Or straight edge. It could be just a straight edge. And if you don't have one, then pause the video because I'm going to keep moving here. All right, so we need to trace a coin, and I did that. I traced a penny on there. And we have to figure out what the radius is, and we can't just guess. So we are going to use these theorems up here. And these theorems will tell you that if you have any two chords, well, actually, back it up. It's not this theorem. I think it's on the other page. Right here, this theorem. If you have any two chords, then you can get the perpendicular bisector of them both. And then we can find the center, and then we can measure the radius. So let's go ahead and do that. So first thing we need to do is just pick two chords. So I'm just going to grab one there. I'm not going to overlap mine just because I don't want to. I'll put another one there. You don't have to be the same length or anything like it. Okay, so now that's the first step. Draw two chords. Second step, construct perpendicular bisector of each. Okay, so you guys remember how to do that? You have to go more than halfway and make a semicircle. And then you go to the other side and make a semicircle. And then those are your two dots. And I'm actually going to grab a pencil if I have one to do this. I'll get this off the table though for the life of me. Okay. And I'm going to connect them. Okay, so that's my perpendicular bisector. It's supposed to be, appears to be slightly off, but okay, we'll go with it. Now we do the same thing on this other one. So more than half. And then go to the other side and do it. And there's my 2 points right there. I'm going to connect those. Keep it straight from the other one. And where they touch, right here, where those two lines hit, is your center. Now, once you have your center, you can figure out the radius. And it looks to be about 1.1, no, 1.2. My eyes are playing with me here. I think it's 1.1 centimeters. All right, and lastly, what is the value of each variable to the nearest tenth? So we got this one picture here, and this is R, by the way. It's hard to kind of read that, but that's R. This little piece here is 3 centimeters, and the whole bottom is 14. So what would we need to do to figure out that R? That's right, Pythagorean theorem. 3 squared plus 7 squared equals R squared. Everybody got that? This is 7. 9 plus 21 equals R squared. Whoa, 21. The heck did I get that? 49, let's try. 58 equals R squared, and R is the square root of 58, which comes out to 7.6 centimeters, because it says nearest tenth. All right, and the last one for today is this fun guy over here. Let's see, what is it? That's hard to even read. Yep, this is 11 right here. So if you look at your triangle here, you have an 11, and you have a Y, and you have a I don't know. But your I don't know, you do know, don't you? Because it's a radius, and even though this is a horribly drawn circle, so this looks tremendously longer than this is 15. So we have Y squared plus 11 squared equals 15 squared, and we go ahead and solve that. .2 is what I got. There's no unit on that, so let's put units. And I'm off the board. Okay. All right, boys. Have a great day. Bye-bye.